Well, thanks so much for having me in this seminar. I'll be talking about, as Peter said, global homological mirror symmetry for genus 2 curves. This is a joint project with my collaborators, Hania Azam, Heather Lee, and Chu Melissa Liu. So the idea of mirror symmetry, which has origins in string theory, the mathematical interpretation of it is that there are manifolds that come in pairs, X and Y, and they each have a complex and a symplectic structure. And the phenomena of mirror symmetry is that there's a correspondence between the complex geometry on X and the symplectic geometry on Y, and the other way around. So symplectic geometry on X with complex geometry on Y. Kontsevich, in the 1994 ICM, he conjectured a homological version, which is that an algebraic invariant encoding the complex geometry on one is actually equivalent as categories to an algebraic invariant encoding the symplectic geometry on the mirror. So the bounded derived category of coherent sheaves, dB_co of X, is isomorphic to what's called the Fukaya category, which I'll talk about at the end of the talk. And the other way around, dB_co of Y is equal to the Fukaya category of X. So first we have to match up the complex and the symplectic structure. So this word global in the title of my talk is—
Can I ask a question?
Yeah.
Is homological, sorry, it's a really basic question. Is homological mirror symmetry the sort of the fanciest version of, or the strongest version of, proposed version of mirror symmetry, or is that would be something stronger than HMS, which would imply HMS?
That's a good question. I think there's some recent work that of implications going in both directions. I think Ganatra has some work with some collaborators. There's different versions. There's a geometric version, which is SYZ mirror symmetry. And given that, you can check homological mirror symmetry, but I don't know if one necessarily implies the other. There's a more classical version of mirror symmetry, which has to do with Gromov-Witten invariance on the symplectic side and period matrices on the complex side. And I think that fits into one of the implications of the three types of mirror symmetry. I think either that implies HMS or the other way around. But there are some implications. I don't know if one is necessarily the strongest. It's kind of matching up different types of like a geometric version, an algebraic version, like matching up the complex and symplectic structures. So I would say that there's kind of like different versions of it, but I don't know if one is like necessarily the strongest.
Okay, all right, thank you.
Yeah. All right, so this word global has to do with the fact that we're considering all complex structures on a genus 2 curve, and on the mirror, we're finding a mirror parameter family of symplectic structures on a candidate mirror for the genus 2 curve. So I'm going to start out, this is kind of more complex geometry. So with the theory of principally polarized abelian varieties. And the reason I'm starting with this is we see the genus 2 curve as a hypersurface in PPAV for short. So this H2, the Siegel space, this is symmetric matrices, complex matrices, which have a positive definite imaginary part. So these actually parameterize abelian surfaces. So the tau gives you the lattice that you quotient by to get a torus, which is a complex torus, which an abelian variety is an example of. So we consider what I call V tau plus. So this is C2 mod Z2 plus tau Z2. And we also consider if you exponentiate the coordinates on that, you get a C star squared where now the lattice X multiplicatively. So this subscript Z and subscript X, these are the coordinates So Z on the V tau plus and X on the V tau. So just to set up notation, gamma tau is the lattice tau Z2 that the abelian variety is obtained by quotienting by that lattice. So the word principally polarized abelian variety, or in this case, abelian surface, because we're looking at two complex dimensions. It's kind of like if you think about polarization in glass, you have some angle so that I think so like the sun doesn't shine in. It's this tau is kind of polarizing your the lattice is being polarized so that you admit a integral 1-1 form, positive definite. So in this case, we have these lattice generators. There's 4 of them. You can think about them generating the 4 loops in the 4 torus. So 1, 0, 0, 1. The first row of tau and the second. These define a basis for the first homology of V tau. And it's through the dual basis that one can build this symplectic form. So this is, you take harmonic representatives for the dual basis, and omega on V tau can be written in terms of those. And through a calculation, you can work out that this symplectic form is related to the original tau through the imaginary part of it. So the imaginary part of tau makes up the coefficient matrix when you write it in terms of coordinates on V tau plus. So the nice thing about this is that because we've principally polarized it, this abelian variety, it admits an ample line bundle. And that ample line bundle is what's cutting out the genus 2. A section of it is what's cutting out the genus 2 surface. So omega d tau, that's the cohomology class of that is the first Chern class of this line bundle. So the line bundle, if you pull it back to C star squared, it's trivial, and then it satisfies a periodicity condition from the gamma tau. And it's a section of this bundle that defines what's called a theta function. So it's a function on C star squared, which is periodic. So it has a Fourier series expansion, which can be written in this way. So tau of the theta 0, 0 tau x. The 0, 0 corresponds to a shift. So this e to the pi I n tau n, there can be shift. You can translate the n in that, and you can also translate the n in the exponent of the x's. So there's 2 ways in which you can translate. So the upshot is we've parameterized the complex moduli for abelian surfaces. It's this Siegel space quotiented out by an equivalence relation, the symplectic integral symplectic 4x4 matrices. But what about sigma 2? What's the complex moduli for the genus 2 curves? So to do that, we use the notion of the Jacobian, which precisely because it's genus 2 maps into a abelian variety of complex dimension 2. So each genus 2 curve we can see as a hypersurface in some V tau. So this is the background for that. We start out again with a symplectic basis, but now we're looking at the first homology group of the genus 2 curve instead of the abelian surface. And the intersection pairing, a choice of a symplectic basis for the intersection pairing is the isomorphism with just C4 with the standard symplectic matrix. And this choice of phi is called the Torelli structure. All right, so this is really the expertise of my collaborator, Melissa Liu. I've been learning. Oh, question?
Can I interrupt with a question?
Yeah.
How do you compute the genus of the zero set of this section as tau?
Oh, that's a good question. Let's see. I worked through this calculation once. I think you have to use the adjunction formula. And I think you can get from that the genus is 2. You can also draw, if you let the coordinates x1 and x2 go to infinity, and you just look at the exponents in this defining the theta function, you can do what's called a tropicalization of the theta function. And if you draw what it looks like, let me see, it looks like this. And then there's the parallelogram defined by sorry, this is a terrible picture, by the lattice. So if you imagine thickening this up, this is kind of like the real part. And you identify like this top and this one and this one and this one. And under the lattice, you can kind of see a genus 2 curve there as well.
Okay, thanks.
Yeah. All right. So the connection with what we saw with the tau above is that it's for the genus 2 curve, that same tau makes up the, the period matrix produces a tau, and then that tau gives you the v tau with which sigma 2 is a hypersurface in. So we define M2 tilde. So this is all of the sigma 2, but with this additional data of the Torelli structure that we don't want to keep in the end when we're just classifying the possible sigma 2. So what we do is we have a symplectic basis now of H1 of sigma 2, which is this choice of phi, and the period matrix is obtained by integrating beta 1 and beta 2 over the dual cohomology class to the alpha 1 and the alpha 2. So this period map from M2 tilde, which is the sigma 2 with the choice of phi, that lands us in the Siegel space, which was these tau that are symmetric and positive definite imaginary part. So this is almost what we want. We want to classify all the sigma 2, but without the data of the Torelli structure. So we have this forgetful map where we, which amounts to quotienting by all of the possible 4x4 symplectic matrices. And this will give us just the complex structure of the sigma 2s. So if we look at what the period map is on this M2 instead of the M2 tilde, so we have this commutative diagram on the top, that's the period map. And on the bottom is the Jacobian. So we integrate, given a point in the genus 2 curve, we integrate over some fixed point x0 to x of the two cohomology 1 forms omega 1 and omega 2. And so that image is in v tau plus. So we now see that sigma 2 under this Jacobian embedding puts sigma 2 as a hypersurface in v tau plus. So we have this correspondence now between tau on the abelian surface and the tau on the sigma 2. And so this gives us a classification of the complex moduli of genus 2 curves. So it's 3 complex dimensional. So we have 6 complex parameters. So it's technically a 3-dimensional orbifold that's dense in this A2. The A2 was coming from the abelian surface side. So I'll just scroll back up. That was the last item here under upshot. This A2 was defined there. So the Jacobian also has six, indicates that we have a six-dimensional real family of complex structures for the genus 2 curves. So this is the picture for the complex moduli on the genus 2 curve. Now we want to think about what is the mirror and what's the mirror symplectic moduli. So to construct the mirror, we have something called Stroming or Yau-Zaslow mirror symmetry, or SYZ mirror symmetry. And to build an SYZ mirror, what one needs is a Lagrangian torus vibration. So if we're starting with V tau, this is a torus. So that's not too, that it's believable that we could construct a torus vibration on it. I mean, a torus is essentially already a torus vibration. So what we do to identify the base of it is can be framed in the framework of, in the setting of tropical abelian varieties, which was introduced by Chan, Mello, and Viviani in their 2013 paper. So they talk about a notion of a tropical, principally polarized abelian variety, where you have now a real 2 torus and you have a positive semi-definite flat metric. For us, omega is positive. So we call this H2 trop, comma P, because we're just considering the fully positive ones, not semi-definite. So how do we build a torus vibration on this? Well, first we have a change of coordinates to R1, R2. So C1 and C2, these are the coordinates in the lattice starting out. So R2 mod omega Z2, this is when we take the imaginary part of our original coordinates on the abelian variety. We have this C1 and C2, but we can kind of straighten out or standardize the group action in the R1, R2 coordinates. Now the group action is just the standard 1 by Z2. So the torus vibration is given by the log norm map. So C star squared, it just takes x1, x2 to the log norm of the coordinates. And this descends to the quotient. So this is our Lagrangian torus vibration on V tau. And the SYZ mirror, it's obtained by taking the same base, and the fibers are tori, and SYZ mirror symmetry, which is shown to be T duality, that's what Stroming or Yau and Zaslow did. That amounts to inverting the radius of the circles of each circle in the fiber torus. All right, so this is the mirror now on the level of 4 tori. What about the mirror for sigma 2? Well, this is, since we're generalizing to hypersurfaces of things that have Lagrangian torus vibrations, it's called generalized SYZ mirror symmetry. So before I say the construction for how to get the generalized SYZ mirror, I want to set the stage for the Kähler moduli space on the mirror, and then justify why this is the construction actually gives us the Kähler moduli of the mirror. So we start out with our tau. This is the complex structure on sigma 2, and we can write it in its real and imaginary parts. B is a 2 by 2 symmetric matrix. Omega is 2 by 2 symmetric and positive definite. So given the decomposition into this B and omega, we can write the sequel space of these tau as 2 by 2 symmetric matrices across this H2 trop positive definite. And we have a map going to the imaginary part. So this is this tropicalization picture above, where we just take the imaginary part of tau. So essentially this map is tau goes to capital omega. So the claim is that when we quotient by integral symmetric 2x2 matrices, what we get is the complexified Kähler space of the mirror, and the image of the map under taking the imaginary part is just the Kähler space. So when we have this B, we started with tau equals B plus I omega, and then we map to the imaginary part of tau, and then we pass to a quotient. When we have a B, that complexifies the Kähler form. But without it, with just the omega, that is actually defining the Kähler structure on our mirror, which I'm calling Y tau. So the claim is that Y tau, with some additional data I'll say in a moment, that is mirror to the genus 2 curve. So we haven't defined Y tau yet, but the claim is that this is the moduli of symplectic structures is obtained by, so this is the space, and to obtain the moduli, we further quotient by this group G. So G is generated by, so it's SP4, integral SP4 matrices where the lower left block is 0. And it's generated by two groups, GL2Z, there's a GL2Z sitting inside of it, and a S2Z. So S2 is the symmetric 2x2 matrices. So the claim is that if we further quotient by this GL2Z, what we get is the complexified Kähler moduli of the mirror. So the idea, in just kind of like the gist of things, like a summary, is tau is B plus I omega. That's the complex parameter. The claim is that this omega, that's the symplectic structure on the mirror. And this B is the B field on the mirror. So the B field is complexifying the Kähler form. All right, so here's the construction, the geometric construction of this Y tau. So this is due to, this theory comes from Abuzaider Rupat-Sarkov, who discussed generalized SYZ mirrors for hypersurfaces of toric varieties. And they also have more recent work, Abuzaider and Aru have some more recent work on that. And Cannizzo and Lau, they also discuss this SYZ process for the case of the genus 2 curve. So the mirror to sigma 2, it's not just this Y tau, there's a additional piece of information, which is V. So V is a holomorphic function on Y tau. So together the pair is called a Landau-Ginzburg model. And that pair is the generalized SYZ mirror to the genus 2 curve sigma 2. So what is Y tau? Well, we start by defining the universal cover. So remember, we have this abelian variety and we have a lattice gamma tau. So before we quotient by that lattice, we have Y tau tilde. So it's a toric Calabi-Yau threefold of infinite type, meaning it has infinitely many facets. And here is the polytope. So it's intersection of half spaces where we have the Xi1 and Xi2 from above, and there's a third coordinate called eta. And the polytope is the graph of eta on this expression on the right. That expression on the right is the tropicalization of the theta function that I mentioned earlier. So this is where the polytope is seeing the fact that we're looking at the genus 2 curve and not just the abelian variety, because we're looking at the graph above the tropicalization of this defining theta function. So if you were to draw what this looked like, it would look like a bowl that is an infinitely big bowl that's tiled by hexagons, and then you fill it up with water. So the eta greater than or equal to, that's the eta direction, is everything above that. So that is the moment polytope. So the SYZ construction produces for us that moment polytope, which is for the universal cover of Y tau. When we quotient that polytope by this gamma tau action, we get y tau. So just for purposes of notation, I'll use later this eta greater than or equal to the inner product of n with xi plus this quadratic form that can be encoded in linear function ln of xi eta greater than or equal to 0. So that's the equation defining the nth facet of this polytope. So we have the inward normals, which is the inward normals to each of these hexagonal facets, which is minus n1, minus n2, and 1. And so altogether they define a fan that's dual to this polytope. And this v that I mentioned, the holomorphic function on y, in the affine toric coordinates, so that's for a toric variety, there's a density star 3. In those coordinates, this v is just projection to the third coordinate. So T1, T2, T3 maps to T3. And over 0, what happens is we get all of the toric divisors, which these hexagons on the boundary of the bowl are the moment map for. So this polytope admits a Z2 action. So it's the standard action in the first two coordinates, C1 and C2. It just adds the vectors coming from the gamma tau action. So omega n, the first column, and omega n, the second column. And the eta has this slightly more complicated group action where we have the quadratic form as well as the inner product with n. So the upshot, finally, to define the mirror to sigma 2 is we take a neighborhood of the toric divisors. So we look at the preimage of 0. We take a small disk in the base and look at the preimage of that. And then so that's equivalent in this bowl of taking just a certain amount of water kind of in the bowl as the moment polytope. And then we quotient that by the Z2 action. And that is finally the mirror to the genus 2 curve. All right, so we now have this candidate mirror that we've built from toric geometry, and we want to know, what about a symplectic form? So what we do is we use, we use a symplectic form that Cannizzo allow you, which is they adapt. So there's Gilliman has a way of constructing a Kähler form from symplectic reduction when you have a toric variety. And he does it in the case of finitely many facets and also for compact toric varieties. So the case of infinitely many facets, Cannizzo allowed described analog where you introduce bump functions. And myself with Azam and Lee, we also have a survey article where we do symplectic reduction for unbounded polyhedra, like we talk about the canonical bundle for complex manifold and how you would do symplectic reduction in that case. So the upshot of doing that is Gilliman's Kähler form would be a finite sum where there's no bump functions, and the sum is over the number of facets. So in this case, we have this potential, and we have infinitely many facets, so it's scaled by a bump function so that locally this sum is still finite. And the ln, that was the defining linear form for the facets. So this is coming from Gilliman, this ln log ln. So the ln equals 0, that defines the nth facet of the moment polytope. And the Legendre transform of this, that defines our Kähler potential. And all of this respects the lattice group action. And so it passes to a well-defined symplectic form on y tau. The fibers of V are holomorphic. And so what we actually get is this symplectic form is a symplectic fibration, which means that when we restrict to a fiber, it's still a symplectic form on the fiber. All right, so this is the construction geometrically of the mirror to the genus 2 curve. So I wanted to talk about what happens as we vary the symplectic structure. So I mentioned about this bowl with its infinite tiling of hexagons. If you project to the first two coordinates, C1 and C2 of this moment polytope, then this hexagons on the boundary of the bowl get mapped down to hexagons on the plane. And this is what it looks like. Well, in what we call phase 1, so I have a result about HMS for the genus 2 curve, where I look at a very particular case. It's in phase 1, and also this A1 and A2, A3 areas that you see in the picture are all equal, and I don't have a B field. So that setting of my result fits in to this picture where capital omega is 2112 and B is equal to 0. But now we're considering all symplectic parameters. So A1 and A2, A3, these are the areas. This is a moment map picture. So this segment is indicating a P1. And the area of A1, A2, A3, that is giving us 3 real parameters. So this capital omega that we originally got from the complex parameter tau, there's 3 real parameters in there, which we see showing up on the symplectic side. All right, so I mentioned this work of Chan, Mello, and Viviani for tropical abelian varieties, and from that theory, you can actually write down this capital omega using the tropical period map. You can write it down in terms of the areas of these P1s, A1, A2, A3. So the area of these A1s is really in correspondence with the symplectic form coming from this capital omega. And the correspondence, at least in what we call phase 1, so the first chamber, is what I've written here. So the omega 1, 1, that's the sum of A1 and A2. Omega 1, 2, which is equal to omega 2, 1, that's the area of A1. And omega 2, 2 is the sum of A1 and A3. What I mean by wall crossing is, as we change the areas of these A's, the picture that is drawn here, so the A1 shrinks down to 0. When A1 shrinks down to 0, what we get is a tiling of squares. And then it starts increasing in another direction, and now we get hexagons that are now going in the other direction. And you actually get infinitely many chambers this way by having things shrink to 0 and increase in another direction. So passing through a place where you get something degenerate, that's crossing a wall in the moment map. And the different phases, these are the different chambers. So this is, I think, really cool. You can actually interpret what I just said as a triangulation of a circle. So the idea is this capital omega, we're going to rewrite in terms of coordinates x, y, z. So we have z plus y, x, and z minus y. And we know that for this omega to be positive definite, the determinant of it and its trace are positive, which is equivalent to z being greater than square root of x squared plus y squared. That describes a cone. So now we have this capital omega written as a cone, the Kähler cone for the Kähler structure on this y tau. So if we imagine this cone and then we take a cross section when z is equal to 1, we get this circle here. And it turns out that through a lot of calculation, you can triangulate this circle. So the picture that I drew above, this is when omega has this form A1 plus A2, etc. So if you set that equal to this omega in the new coordinates with z, x, and y, what you can do is solve some equations, I think linear, and I think they're all linear equations. And you see that for the a's to be positive, it cuts out this triangle that is labeled I. When the a's go to 0 and then you cross into another wall, you get another chamber and you have a new set of coordinates of a's. And for those to be positive, it corresponds to relations which cut out this phase 2. So you keep doing that and you get these triangles, 2, 3, 4, you get infinitely many. So this is the picture for the real part of the symplectic form on the mirror. But remember, on the complex side, the genus 2 curve, it was complex dimension 3, the space of parameters. So that's 6 real dimensions. The 3 additional parameters, so there was this b that we had on the complex side. The b on this case, on the symplectic side, also acts as complexifying, and it complexifies the symplectic form. So B, remember, is a 2 by 2 matrix. So on a fiber of this symplectic fibration, we get the dual abelian variety. And the B field on that is just the same B matrix, which was the real part of tau. And it's written in terms of these R coordinates with respect to which the lattice action is standard. But the B field on the total space, this y tau, we have this third coordinate. You can write it down the same way you would write down the symplectic form in terms of the moment map coordinates. So you have, like that. So this eta with the superscript b, it's just like the eta was for omega above a moment map coordinate for omega. Eta b is a moment map coordinate with respect to b. So b isn't necessarily positive definite, it just has to be symmetric. So I believe this is the setting of a pre-symplectic manifold, which there's a paper, let's see, there's some classical work that has been done on pre-symplectic manifolds, but it works very similarly to symplectic. You can still have a moment map, you still have a torus action, you still have this A to B. Okay, so we now understand the genus 2 curve and its complex moduli, its mirror symplectic manifold, which is a symplectic vibration, and its scalar moduli. So now I'll do a very brief description of the Fukaya category. So the objects in the Fukaya category are pairs of a Lagrangian in the total space, as well as a unitary connection one form. So the way you build the Lagrangians in the total space is you start by looking at the pre-image of fiber over -1. And this turns out to be the SYZ dual abelian variety. So V tau check, that's the SYZ mirror of the original V tau. That is now a fiber of this Y tau. So you start with a linear Lagrangian in the fiber. So it's defined by this linear relation. Theta is B minus KR. So R is K is like a slope. So R is a coordinate, theta is a coordinate, and B is a shift of the Lagrangian. So it's an analog. If we were instead in the 2 torus instead of a 4 torus, it would be a straight line in the square, a straight line of slope K that's allowed to be shifted by some amount B. So this is the Lagrangian that we take in this fiber here. And then we parallel transport it around this U shape in the base. So we have a symplectic form, so that means we're allowed to do parallel transport with respect to it. And the Lagrangian in the total space is topologically the Lagrangian of fiber times bar. So it gets transported around this U shape around the singularity. And I've also pointed out over 0, I mentioned we have the toric divisors, these hexagons on the boundary of the bowl. If you look at the critical locus of that, you get the banana manifold. So this is those 3 P1s that were area A1, A2, and A3. You can see them here sitting as the critical locus of the over 0. So a Lagrangian, this is something on which the symplectic form is 0. It's a half-dimensional submanifold on which the symplectic form is 0. And because we have a B field, we also have to keep track of attaching to that Lagrangian a unitary connection one form, which has a property that its derivative is the B field. So it's the one form, you take the derivative, you get the B field restricted to the Lagrangian. So this connection one form is only defined on the Lagrangian. So this equaling the B field only makes sense on the Lagrangian. And so we worked out that this connection one form is equal to, so it depends on the monodromy. This F1 and F2 is the monodromy. Since it's some parallel transport with respect to the symplectic form, it fixes the moment map R1 and R2. So this F1 and F2 is what gets added to the angles. That's the monodromy. So we have this term due to the monodromy in the first term, and then the second term is what the local system is in a fiber. So this is just to make sure that over -1, we get the right local system in the fiber, where these A's are constant. So the morphisms in the Fukaya category on the chain level, they're intersection points. Now that we have this additional data of a line bundle on the Lagrangian, we have the chain groups are a direct sum over the intersection points, but now of Homs from the line bundle of 1, so EJ, and the line bundle EK, at the point P, they're each just a copy of C. So this is just a complex number. So at each point P, we assign a complex number, which is what like 1 gets multiplied by in these 2 lines of the line bundles. And the differential counts bigons. In a fiber 4 torus, there's no differential. But in this Y tau, in the total space, we do see bigons showing up. So we have these 2 U-shaped curves. If we project them down to the base, this is what they look like. And we see that there are bigons showing up. When we have 2 of them, we now have intersection points which bound bigons. So I use capital M to indicate that it's happening on the total space, and mu to indicate structure maps that happen within a fiber. So this M1, we input something which is in this thing here. So the rho times P, rho is an element of the Hom, so it's what we multiply by in the Hom from the 2 line bundles, and then P is the intersection point. So this is here. So P is an intersection point lying over this point here. And what we do is we count bigons. So we count the moduli space of bigons from, sorry, PJ plus 1. Or actually, let me just. I was trying not to get too bogged down with having too much notation. So this is the P. So the input point is P, the output point is PJK, which is the intersection points of LJ and LK. This is counting bigons from P to PJK that live in homology class beta and are pseudo-holomorphic with respect to a regular, almost complex structure J. And the addition of the B field is deforming the structure maps here, because instead of omega tau, instead of weighting by just the area of the beta, we're now weighting by a relative cohomology class, with the omega tau C is omega plus IB. And so when we weight by the relative cohomology class, we have like a relative version of Stokes' theorem, and we keep track of these connection one forms. And composition, it's the same definition, but instead of bigons, we're counting triangles because we're inputting 2 points and outputting 1. So we have triangles between the 3 intersection points. And we have a Leibniz rule. So if you take the derivative of the product, it's the product of derivative of the first one plus the product of derivative of the second term. And then the final statement, the global homological mirror symmetry statement, is that this HOM, these two HOMs on the right-hand side are isomorphic. So they're each computed by a resolution. These are the HOMs. We show a fully faithful embedding of so dB co of the theta divisor to the Fukaya category of y tau p. Specifically, we pass to the cohomological version, which is why the HF, the HOMs are computed as a resolution by this differential. So we show a fully faithful embedding here, where on objects, the line bundle of degree J tensored by a shift of an amount AJ gets mapped to this Lagrangian LJ with a local system EJ, which had the definition of AJ in it. So that's the mirror correspondence on objects, and a fully faithful embedding means that the morphism groups are isomorphic. So this diagram tells us that the morphism groups are isomorphic. The first two downward vertical arrows are HMS on the abelian varieties, which we show in our paper directly, although it was already known more generally by Kenji Fukaya. He had defined the functor going in the other way, from the Fukaya category to dB-co using more advanced machinery. But so the first two arrows are isomorphic, and the first square commutes by the Leibniz rule. So there's some work that goes into that. And therefore, the third downward arrow is the isomorphism, and that gives us this fully faithful embedding homological mirror symmetry result for the genus 2 curve and its mirror. Thanks so much.